Going into the last section of Unit 1, we'll be dealing with irrational numbers and decimal representations. Now, for some of the material we're going to look at, we're only going to look at it for historical purposes and not try to master the material. These are much higher level math areas than what we want to cover. So again, definitions and basic concepts, the irrationality of the square root of 2 and proof by contradiction. We'll do that part historically. Operations with square roots, the irrational number pi, phi, and the letter E. And let's go on to a definition in set builder notation. An irrational number, x, is such. X is a number represented by a non-repeating, non-terminating decimal. And we've covered that now a number of times. Now, something I want to give you, and I'd like you to sketch this in your booklets. Now, this is to be a square where the sides are 1, 1. All the sides are 1. And this is the diagonal of the square. So we're wondering, what is the length of this diagonal? Well, for this, since we have a right triangle here, we can use the Pythagorean Theorem, which is a squared plus b squared equals c squared. And in a sense, this could be side A here, this would be side B, and this is side C. Remember, these are the legs adjacent to a right angle, and the side opposite is the hypotenuse, if you remember that from the Pythagorean Theorem. So now we're going to solve for the length of C by substituting. Well, A is 1 that we're going to square. B is 1 that we're going to square. And we don't know c squared. But 1 squared is 1. 1 squared is 1, so this adds up to 2 equals c squared. Now to find c by itself, we take the square root of this side, and that is c, and the square root of this side, and that is the square root of 2. So the diagonal of any square is the square root of 2. So this is the background of our closest thing that we're going to do to a proof of what is the square root of 2. Now in your notes, we're going to take a look at the various properties of dealing with operations using square root. And again, we're dealing with non-negative real numbers, a and b. So if we are multiplying the square root of a times the square root of b, we can put them under a common radical sign. And this would be the actual product, ab. So we're allowed to do that. Now, we want to give you, again, a little bit of background on radical numbers. So, we want you to include this in your notes. So, of course, we have the sign. This is called the radical sign. Now, you notice there's a little notch here. And sometimes you may see a little number there. Well, you will never see a 1 there. if there is no number there, the number that is imagined or by theory is there is 2. So that gives you the square sort of related to 2. So with no number in this little notch area, this is a 2. Now, numbers higher than 2, like 3, you could see a 3 there, a 4 there, a 5 there, but they would have to put these numbers there. And what is the name of the number that goes there? Well, again, take some notes on this. Now, first of all, this is called the radical sign. The radical sign. That's its symbol. What goes in that notch is the index number. Take some notes on this. These may be quiz questions. The index, just the word index or index number. If there's no number there, it's a 2. And what goes under the radical sign, like you might see a 2 there, or 23, or whatever, is called the radicand. So, again, some background and vocabulary building. Now, when we simplify radicals, in order to have them simplified, you want to have the smallest number possible under the radical sign that is not a perfect square. And I'll give you an example of it here so you can see it. Take some notes on this. Let's take the square root of 8. Now, as we look at the square root of 8, is this the smallest number that could be under the radical sign? And the answer is no, because referring to the previous slide, we could divide the square root of 8 into a perfect square 4 times the square root of 2. So if you multiply these radicands together, you get 8. But 8 can be factored into a part that's a perfect square and another part that's not. So this square root of 4 would become 2, the square root of 2. Now this is in its simplified form. Here it is not. Here it is. So that's what they're referring to. Now, also, when we have a radical, we can never have it in the form the square root of 1/2. That is, have the radicand as a fraction. So the radicand has no fractions. And the denominator does not contain a radical. So you couldn't have like 1 over the square root of 2. You can't have a radical in the denominator and say that that example you're looking at is simplified. So these are skills we're going to work on. This is some background information. So we're going to do what we've just illustrated and simplify this. Now, the policy I like to follow is you write the example, and you'll be doing this in your homework log, and then underneath it put 2 radical signs, because you want to simplify this. And you might say, what's the greatest perfect square factor of 32? And you might say, I have no idea. Well, let's do this. 32, going to divide it by 2, and you get 16. You say, wait a minute now, 16 is a perfect square. So on the left radical sign, you'd put 16, and keep in mind there's a dot there. We don't have to show it. And then there's a 2. So 2 times 16 is 32. You've teased them apart into the largest perfect square under the radical sign there, and then you go square root of 16 is 4, the square root of 2. So you have simplified this. Pause is needed. And there they're showing you the steps. Now, by the way, going back one, we want you to write this in your booklet as 1 pp, 1 PowerPoint, the first example. All right, now another background rule is for non-negative real numbers, a, and positive real number, b, if they were in fractional form like this, you could put them under a common radical sign. Or if they were like this, you could go backward in a sense and separate them into radicals. But remember, here you can play with them. Let me give you an example of this here. If you had under the radical sign the square root of 12 fourths, it might have been like this. 4 will go into 12 3 times, so you then have the square root of 3. Okay? You've simplified that a little bit. Or if this were 12 thirds, another one, you would go, 4 goes into 12 4 times, and you would get the square root of 4. And then the square root of 4, you'd simplify that as 2. Here, this would be irrational. The square root of 4 is rational because this operation sign, the radical sign, is take the square root of 4 and you get 2. So now we have this that we are asked to simplify. This is, write this in your notes, example 2pp as a reference. So we can take it the square root of 7 over the square root of 9. So the square root of 7 is irrational, but the square root of 9, the operation takes us to 3. Square root of 9 is 3. So now you do not have a radical in the denominator. You have simplified that. And to check it out, here we go. Now, for this one, and this is example 3pp, we have 5 in the numerator, but the radical, square root of 3, in the denominator. And they're asking us here to rationalize the denominator. That is, get the denominator to be a rational number. Right now it's irrational. Well, the technique is, again, we have a fraction. We can multiply anything by 1, but we're going to choose our 1 such that it makes the square root of 3 a rational number. So the technique is usually just take the square root of 3 over the square root of 3, which is a 1. We're allowed to multiply anything by 1 and not change its value. And now we get 5, the square root of 3 in our numerator. We get the square root of 3 times the square root of 3 is the square root of 9. That we know simplifies to 3. So we've now gone from an irrational denominator to a rational denominator through the process of rationalizing the denominator. This is a great word because it means exactly what we're doing. And here they're showing us in detail. All right, let's go on. Okay, so for example 4pp, we want to add and subtract square root radicals. Now, keep in mind, again, you're learning some of the methodology for mathematics. Here we have 8, the square root of 7, plus 2, the square root of 7. Now we can think of the square root of 7 as the letter A, for instance. So if we had 8A plus 2A, we would end up just adding our numbers and get 10A. So if we had 8 apples and 2 apples, we'd have 10 apples. Well, here we have 8, the square root of 7s, and 2, the square root of 7s. So the process, if the radical part is identical, we just add what is in front, and we get 10, the square root of 7. Now we can do that so long as our radical portion is exactly the same. Now as we look at B, we see the radical portion is not the same. So we have to go back and see if we can simplify these and put them into a form that has the same radical. So to do this, we need to use a technique we had a little earlier. We're going to tease the 50 apart, 2 sets of radical signs minus 2 sets of radical signs, and we want to put the largest perfect square factor that we can get out of 50. So if we divide it by 2, we get 25 and 2. And then looking at the 18, what's the greatest perfect square factor? 9 and a 2. Oh, okay, that wasn't too hard. So square root of 25 is 5. The square root of 2 minus the square root of 9 is 3. The square root of 2. Now our radicals are the same, so we just deal with the numbers. 5 minus 3 is 2, the square root of 2. So it may look a little daunting. We're using a skill we had a little earlier. And the ones that you're going to have shouldn't be too difficult to work with. Probably this level of difficulty. And there's the solution for A again, and the solution for B. And hopefully the narrative we're giving is useful as you see how it goes. All right, let's go on to some famous irrational numbers. Now, much of this will be for historical purposes, and then a little bit of something we're going to use in the next section, the next unit. Now, one of the famous ones, of course, that we deal with is pi. There is a symbol for pi. And one of the quiz questions I like to give is, what is pi a ratio of? And if we make a circle, see if I can make a nice circle here. And that would be the circumference of the circle. And then this is the center, and then a line through the center connecting portions. This is the diameter. So the diameter and the circumference. And pi is a ratio of the circumference to the diameter. And there are a couple of other relationships that we indicate, like 22 sevenths is one that approximates pi. You'll see that sometimes. And then there is, and these are just approximations here, 3.14 would be a decimal approximation. And then if you extend it even more, there's our 3.14. It continues, there's no pattern, and it doesn't terminate, so that's why we consider pi irrational, but then the equal pi. So these are approximations. Your calculator sometimes has a symbol pi that would be much more accurate, but if they tell you to use 3.14 for pi, that's what you are to use. So you get the answer the software is prepared to accept. Okay, that is some background on pi. Now, another famous ratio is called the golden ratio. The symbol for this ratio is this Greek letter here. Now, notice we've used one when we talk about an empty set and things, but this is sort of a oblongish zero, or it's thickened here. I don't know how they do that. So sometimes you see this too, but that's a different symbol. This is for something we use in sets. We'll be doing this later in the term, but this is phi. P-H-I. It's a Greek letter, and they're a little bit different, although it can easily be confused. So again, we're not going to ask you test questions, just to familiarize you with something historical. Now, this is called the golden ratio, and we see that often in buildings that use, as they build a building, the golden ratio in the Parthenon in Greece. And if you worked it out, it would look like this. This would be an exact answer. 1 plus the square root of 5. It's irrational because of the square root of 5, all over 2. And if you put this into your calculator, you get something like this. Again, it continues, doesn't repeat, and doesn't terminate because of its being irrational in this part. So we give an approximation of it. What is this called again? The golden ratio. And it's the top part is sort of a little longer than the bottom part here. So that's why it's 1.6. So this would be like 1.6. I'm just to 1 here. I may have not have drawn it right. Okay, historical value here. Now, another super famous number, and again, you may never have heard of it, but is the letter E. Now, our textbook shows how they go about to get this. This was developed by a mathematician, and his name is spelled E-U-L-E-R. You might pronounce it one way, but the correct pronunciation is Euler, O-I-L-E-R. That's the correct way to pronounce that. I don't want to say how I would, because I would pronounce it more in the English way, but the way to pronounce it, Euler. Now, since his last name began with an E, this number here was given the name E as a tribute to the man who developed this back in the 1700s. In fact, we may give you a little bit of background on Euler as part of our lesson here when you get to class, just to show you how important he was and for historical purposes. Now, we use this letter E later as a natural exponential and natural logarithmic functions. We'll be using that, so we're spending a little time emphasizing it, but basically here for historical purposes. Now, we usually round the number off to 3 decimal places, so E is often 2.718 historically. Okay. Now, we're going to write some examples in our booklet as part of our notes. And some of these are not listed. So if they're not in our booklet, you are to write them in your booklet. So for instance, the example 1 is not this one, but in your notes part, write this. But this would just be example 1 with no PP. The textbook that I got these from had some of these others, and we want to use them as background and examples. So you're going to write the square root of 27. You want to simplify that. You're going to put 2 radical signs. Now, what's the greatest possible perfect square factor of 27? And if you recall, 9 times 3 is 27. 9's a perfect square, so this becomes 3, the square root of 3. So we're starting off with a rather easy example. Now, you could put that into your calculator and you get this approximation. And if you would, write this also. Now, as you do so, put little wavy lines there. This might be a quiz question now, but I would say example 1 from the PowerPoint slides, as opposed to example PP. And this would be what you would write. And again, you want to practice the root key. Sometimes it's a second function. I'll have this symbol on your calculator. Sometimes it's a first function. But if you're having trouble using a calculator and finding the square root of something, ask me, and I will give you some personal instruction. Now, here are some others that are not in your booklet yet, so we want you to add these. And I believe, yes, this one is in your booklet, is number 4. So we want to coordinate that a little bit here. In your booklet, this is 4, so you can use your booklet. So let's do these. So this is the square root of 25 over the square root of 9, which is going to be 5/3. This one was pretty easy. This will be the square root of 3 over the square root of 4. Square root of 3 is irrational, but square root of 4 is 2. Here we have the square root of 1 over the square root of 2. Now, since the square root of 1 is 1, but the square root of 2 is irrational, so here we have to multiply, and we can change that to 1 over the square root of 2. We have to multiply this fraction, because we want to get rid of the radical in the denominator. We want to rationalize this denominator. So this will become multiplying it by 1, and we're going to use the square root of 2 over the square root of 2. So this becomes 1, the square root of 2. And then square root of 2 times the square root of 2 is the square root of 4, which becomes 2. And usually we don't write that 1. Now, no, there is a 1 there. But we can just take it away. There we go. So these are some examples. This is number 4 in your booklet. And we'll see what the book does for these as well. Put back there a little bit. Okay. So again, this is the proper representation of 1 over the square root of 2. You cannot have a radical in the denominator. You have to rationalize that denominator, and that's what we did there. All right, let's take a look at this one now. Now, this is number 5 in your booklet. Here our radicals are the same, so we just add the numerical part, and that would be 7, the square root of 6. Now here we did one like this. This is subtraction. Radicals are not the same, so we put 2 radical signs. We have to simplify them. And 18 is 9 times 2. And 32, we did that already, is 16 times 2. So square root of 9 is 3, the square root of 2, minus 4, the square root of 2. And now our radicals are the same, so we're going to get the square root of 2. 3 minus 4 is a negative 1. But often we don't write that 1, so we get negative square root of 2 as our final answer. So again, show the work, because this would be your background of what to do in something like this. You're going to be emulating the protocol for solving examples like this. Hopefully you follow what I'm saying here. And there it is. Now you can pause on this page to see it, and this is I got this from the textbook. Okay, now this one, as we mentioned from higher mathematics, that is what we call an infinite series, converges to the ratio of pi over 4. All right? Again, you don't have to know this, and I don't believe you have this in your booklet. Let me check. But it's not needed. Historical purposes here. And they give you more detail. And then they also go toward the bottom here to show you the detail of the golden ratio, the calculations. This is just for historical purposes. And then Fibonacci's sequence, again, historical purposes. Some pretty heavy math, and this was to show us a little bit of how great mathematicians worked these out in the past. And then there is Euler's lesson, and in class I'm going to show you a little bit of the background of who Euler was and what he contributed to math for historical purposes. And this is, again, historical. And how they get E. Now I'm going to go back one as we finish this, but I just want to review with you that example 1 in our booklet, as is listed there, shows using a calculator to approximate square roots. Now, I've given you the answers there as well, but you should try these on your calculator. One that we didn't do, and I want to work with you, is applying a formula for pipe flow. Let's do that one now. All right, this is example 2 in our booklet, and it's just to see if you know how to put things into your calculator. So here they're defining capital D as 1 1/2, which is 3/2 or 1.5. They're defining lowercase d as 1/2 or 0.5. So I put that in as 1.5 divided by 0.5 in parentheses. And then I use the caret to introduce my power of 5. Got an answer, which was 243. And then I took the square root of that, and I got this. Now, another technique that we should mention is, suppose they asked us to round this off to the 4 decimal places. So how would you do that? Well, you go 4 decimal places right here. Now, what we have to do is look at the 5th decimal place, which is a 5. If it's a 5, the rule of rounding is you drop this, but add 1 to the 4. So our final answer would here, and this would just be approximation, 15.5885, as we add 1 to the 4 and we drop this. Now if this were 4, we would just drop it and not add a 1 to the 4. So a little background. Now, to wind this up, I'd like to do, let's say, the first 12 examples. We don't often do this, but just to get a little practice. We want to identify these first 12 as to whether they are rational or irrational. And this is in your booklet, so all you have to do is put like the letter R for rational or I for irrational next to each one of these. And if they are quiz questions, you will have the answers right at your fingertips. Remember, our quizzes are a check that you've taken good notes and understand the lesson. So here, this is a traditional fraction. This is rational. Traditional fraction, rational. This is a radical. It's not a perfect square, so it's irrational. Not a perfect square, a radical, irrational. This is in its decimal form, and it terminates, so it's rational. Decimal form terminates, rational. This one shows a repeating pattern, so it's rational. Repeating pattern, rational. We said pi is irrational. E is irrational. Where this might be an approximation of pi, it's not pi. It terminates, so this is rational. Again, an approximation of pi, but it's a fraction. It is rational. Okay. Again, if you had the textbook and we were doing out of the textbook, we're doing our homework. And again, it's only 20 examples. Here, this goes up to like 120 examples. So we wouldn't, of course, do all of these, but 20, I think, is a good representation of what we're doing. All right, we'll wrap this up at this time.